population of the country, but it is a very small country. So Belgium has a small sea coast, and we are surrounded by a couple of countries. So here is a small country, Luxembourg, and that's France, Germany, and Netherlands. So we are kind of in the middle of Europe, and Brussels is there, which is the kind of the official capital of European Union currently. Right. So, and we sit somewhere there in the east coast of or east of Brussels. So this is the perspective. I heard from your HOD that you guys most of you are in bachelors. I just wanted to tell you what it looks like to do a master's in either Europe or US or Australia, Canada, places like that. So this is the industry, typical industry, right? So industry is, this industry is in Belgium. So I know very much more about Belgium. So I'm going to, but in general, this is how the industry looks like. So it's a pharmaceutical industry. So actually, headquarters of Johnson Johnson Pharmaceutical Division is in Belgium, which I had worked, as Anil told, for 4 years as a senior scientist and later on as a manager. Then we are also very big on plastics. The coast side, which is Antwerp, it's called Antwerp province and Antwerp city. There's huge amount of plastic industry there because it's also closed, right? So you get oil, and from there you can directly pump into the companies or into the factories, and you can make plastics, all kinds of plastics, general common plastics like polyethylene, polypropylene, but also specialty plastics like Dyneema fiber and stuff like that. There's also a big paints industry. Many people are doing fibers. There's a company called Donaldson, which is doing a lot of fibers based on plastic fibers for air filtration, water filtration, oil filtration. Currently, there is a lot of bio industry that is being developed and also coming up because we want to go into more renewable energy and renewable resources. So we are getting into more bio industry. Many of the chemical engineers also go into management and consultancy because whenever you go into management consultancy, they have to consult to or manage some companies, right? So one of these sub part of the companies are chemical industry. And for these companies, actually, if you have chemical engineering background, it's a lot more advantageous for you because you talk the same language, you know what they want, and you can also consult them in much more better. Same goes to software. I personally see many Indian students who are software students who have come to Belgium to work for, let's say, pharma industry, where I was there. I think there were like around 100 Indians working there, and they were developing software for pharmaceutical industry. And I could see the people who were progressing much more higher or much more faster in their job was the people who had chemical engineering background, because these people could nicely talk with the local chemical engineering research employees of the company, and they could translate their language to software people's language much more easily. So they automatically became people who are going up in the ladder. So this is the salary. So it depends, right? So it depends. If you start off with, you will start with around 50,000, 45,000. This is before taxes, and the taxes are very high in Europe compared to North America. Europe, the taxes can go up to 50%. So typically you start here, and after a couple of years, let's say after like 5 or 10 years, depending on how fast you are going up, you can go up to around 90,000. Of course, there's also much higher. This is kind of an average salary that is there currently in Europe. In North America, actually, if you translate euros to dollars, it will come back to the same thing. 50 euros is around $70,000. So this is Canada and US. It's something like this. This is for chemical engineers. This is for chemical engineers. And chemical engineers are actually one of the, if not the highest, one of the highest paid students in almost whole of North America, Europe, Australia, New Zealand, these places. Because they are making something, right? It's very essential products that you're making. And I don't know if you know it, you should talk to your professors that without chemical engineering, there is one product in the world which chemical engineers make that without that, half the world's population will not be alive today, right? And that is ammonia. We have to manufacture ammonia, and ammonia is what is used for growing plants. And if we did not have ammonia, half the world population, means 4 billion, now we are around 7 point something, 4 billion people would not be alive today. Just simply cannot be alive today, right? Because of the amount of food that we're producing, we can sustain up to around 10 billion people on Earth now. And in Belgium, whatever I've seen from last 10, 15 years, we get approximately, in at least doing my PhD, we were getting around 40, 50, 60 students a year. It was always, of course, going up and down. Almost 100% of the students got into chemical engineering who wanted a job. If some people told, no, I want to do a master's, I want to go and do a MBA or something, of course, these people were very small. So only like 10% of the students did that, went for a PhD or went for a MBA. But 90% of the students who were in the market for a job ended up in a chemical industry. So chemical industry is extremely, extremely good here. I know from my friends and from my experience in Canada and US is the same story. They are paid quite good and the placement is also extremely good. Since you guys are, okay, it's coming now. Since most of you are masters, right? So sorry, bachelor students. So of course, if you want to come out of India, or if you want to stay in India, also we have very, very good institutes, like especially IITs, NITs, Bets, all these places for both masters and PhD. Language. So if you want to come out, you should always watch out for language, so you don't waste time and stuff like that. I'll give you a couple of suggestions for this. One is if you go to North America, of course, it's US and Canada, so there it's English, so you have no problem. But if you want to go to US, you have to write GRE. And you have to prepare your GRE when you are already in your third year of your engineering, third or at the beginning of fourth year, so that halfway through your fourth year, which is like the seventh semester, when you finish your seventh semester, you should have your GRE scores so that you can apply. It takes around 6 months to a year for the whole process. You apply, you get a position, then you have to arrange for the money, then you have to go get the visa, and then you have to go there. So that is one big thing. So TOEFL, right? So one is GRE you have to write. The other one is you have to write is for English you have to write either TOEFL or IELTS. In Canada, in some universities, there are I think 7 or 8 universities. In some universities they ask GRE. In some universities, they ask only TOEFL or IELTS. So that is one of the advantages in Canada. How do you apply? Normally, you apply to a professor or to a university. So in some universities, both in US and in Canada, in some universities, you can directly write to a professor. If the professor says, yes, I like you, you can come. Then you have to kind of formally go through the university, but you know that once the professor says yes, you are done. In some cases, the professor might say yes, but they will say, okay, I like you, but you have to go through the university procedure where they will have some procedure. They will have a ranking on the year. So if you apply, let's say for next year, 2021, then they'll have a ranking saying like, okay, this many students have applied. This is the criteria that we have selected. It's always not only marks is this criteria. Marks is one of the criteria, big criteria, but also they want to see other things. What is your curricular, other extracurricular activities? Can you write a good motivation letter? How is your English? If they ask GRE, what is your GRE score? So these are all they have some criteria. And they will also sometimes in some universities, there is also criteria like we want so many people from Asia, in Asia, we want so many people from India. So that also might kind of get you in this selection list or get you out of the selection list. So this is English. So be careful here when you're keep this in mind about GRE and stuff. In Europe, most of the time they don't ask you GRE. I don't think anywhere I heard till now that they ask GRE, but they do ask IELTS or TOEFL. So most of the time it's better to do IELTS than TOEFL because IELTS is really recognized everywhere. TOEFL, sometimes they recognize and sometimes they say you have to do IELTS. Of course, you can go to UK, right? And also to all these countries where masters. So masters is in English. So in UK, it's in English. Of course, bachelor's is also in English. In Switzerland, the master's is in English. In not all universities, some. In Sweden also. In Netherlands, both bachelor's and masters are in English. And masters, of course, is in all universities, it's in English. And Belgium, all masters are in English. Bachelors is still either in French or in Dutch, depending on which part of the country you are. If you go to Germany, Denmark, France, it might be that in Germany some universities do give masters in English, but all the other countries like Spain, Portugal, Denmark, Italy, France, all these people give only in their local language, right? So you have to have the language and go there, or you go there, get the language, and start your master's program. And of course, there's also Australia and New Zealand, which less people try. Australia, I'm pretty sure many people are trying to go, but New Zealand also have one or two very good universities, and also a very pleasant place to stay. And also they're doing very good research. In all these countries, these two are a bit exceptional. I'll explain you why. Because in all the universities, you have to pay for your fees, right? You very rarely you get scholarship. So in US you do get scholarship. In European countries, it's very rare that you get scholarship. In Europe, there is something called Erasmus program. If you come via Erasmus program, you are going to get some scholarship. If you don't come via this program, then barely you have any scholarship. In US, US and Canada, you do have a lot of universities which do provide scholarship, but it's highly competitive. So if you're good, of course, you're going to get it. Also, as I told, there is a criteria. It's not only your marks, but also other things that you are doing in your life. So instead of in the summer, instead of sitting and watching TV, or which you can also do, it's fine. I would suggest try to do some work either in NGOs or in some industry or something, so that you can show, well, you do it for your own good, so that you get exposure of what you're doing in your life. And also, it's very good on your CV. So you have to also play this card. So you'll get experience, and you can put it in your CV that I worked in this and such industry or such and such NGO for my internship, or in the summer 2 months. That also boosts your CV when you apply. So in US and Canada, there is two kinds of research, two kinds of masters. One is normal masters, like how you are doing your bachelor's now. You go sit class. I think there's some 60 credits you need to take. And the last semester, you have a 6-month project when you like a research-based project with which you need to finish. The other one is called Masters, Research-Based Masters, which is also in I think in IIChE and IITs, it's there, where actually you take only, I think, 20 credits or 16 credits or something like that. And so which is like a semester to semester, and the rest of year or year and a half, you do research. And for that, they pay you actually. So that's the advantage between doing masters in research as compared to normal masters, is that in masters for research, of course, somebody is paying, either the government is paying for the research, or some company is funding the research. And then you go there, you finish your 6 credits or 16 credits or 20 credits, which is your core chemical engineering, advanced chemical engineering topics, or some topics that is useful for the research that you're going to do later on. And then you do your research, and then the big, like 40 credits or 50 credits would be on your research topic, so which you publish if possible, and you have to write a thesis. So that is what I did in Canada. So I could not pay for the thing, and they paid me, and I could pay and still you have to pay the fees. You pay the fees, but you can kind of manage with your scholarship to pay the fees and to survive. That is the advantages that you have. Disadvantage between North America and Europe is, so North America, the fees is relatively high, especially in US, the fees are really high, right? The fees can go up to 50, 60,000 dollars a year. In Canada, it's relatively okay. I think you pay around $5,000 to $10,000 a year. And in Europe, it's very less. I think UK is the highest. It's same as Canada. It's around 10,000, 15,000 a year. If you come to Netherlands, you pay, I think, 8,000, 9,000. If you come to Belgium, you pay only like 3,000 or 4,000. France also very less. So some countries are very less because it is funded by the government. And there is no private institutes here, private universities in Europe. Maybe in UK, probably, I'm not sure. In US and Canada, there are a lot of private universities and a lot of government universities. If you go to government universities, let's say for University of California, then you are going to pay less fees. And if you go to some private college, then you're going to pay a lot more fees. So that please keep this in mind before you apply and try to do which is good and which is not good. So things that you should remember: masters. If you go for masters based normal masters, course based masters, or masters with uh, research. So two options. And then the language, you have to watch for language, which country, and just don't apply to anywhere because you have to watch for the language. Also see what is the criteria, how long does it take. In Europe, it takes anywhere between 6 months to a year for you to prepare and come here, relatively much faster. And also getting visa is relatively okay compared to US or Canada. So language, this one, and also fees, and what kind of research you want to do, because it might be that you want to do some particular kind of research or some particular kind of masters. Then you have to choose based on the country and based on all the criteria that I've told you. And one big advice, because I get a lot of emails from Indian students, I try to reply, but it also gets annoyed at some point, is that before you write to any professor, please look into their website, look at their latest papers, because these are the papers that they are currently doing research into. Then write to them saying, oh, sir, I want to come there. And also don't be too polite also, because it also seems like you're bobbing down too much. So you just be polite saying, oh, sir, I want to, I'm looking for my master's. I looked into your research. I read this and paper from you. It finds interesting for me. If you're honest about it, I would like to do a master's with you. Can you let me know if it's possible, or what is the criteria, and how can I start this education? And then it'll be fine. Okay. So that is what, just brief explanation of what you can do for your master's and stuff, where you can go in industry. Now I'll get into research. I'll explain you a few things that I'm doing, and then I will get into my topic that I had actually presented, or I'm going to present on self-propulsion. So this is the lab. So my lab name is Structured Soft Matter Lab. So soft matter is anything that has a lot of space in between, like your skin, your polymers, wood, everything, right? It's really not like metals. I'm not working in metals. I'm working mostly in colloids, and also cells also sometime. This is where I am. So in Belgium, I am on the east side of Belgium. At the university is east side of Belgium. I'm staying in the middle of Belgium. That's how the Hasselt University, where the university is named after the city called Hasselt. And the old campus is inside, and the new engineering campus is somewhere outside. And that's how the university looks like. It's written in Netherlands, or in Dutch, Universiteit Hasselt. It's Hasselt University. There are around 6,500 bachelor students, and we have around 600 PhD students working. In the university, I am actually working in an institute called Institute for Materials Research. It's again in Dutch, but it basically says Institute for Materials Research. That is IMO. So one topic that I'm working currently is biodegradable polymers. As you can know, we have this pollution in ocean. In that case, it's mostly 50% of the pollution, plastic pollution in ocean is from the car tires, actually, or the tires of automobiles. The other 50% is all the other polymers that you use in your household things, and also people use in commercial situations. So one problem with the biodegradable polymer is you can't break these polymers, right? It will stay forever, almost forever, like 1,000 years it can stay without breaking down. So one idea was like, what if we now make these polymers, like, so these are individual monomers, let's say, and then we add this kind of rings. These are cyclic ketones. If you add them and then make a polymer, which is something like that, right? Then you have polymer, and then you can take this polymer, use it to whatever you want. You throw it out or put it in some specific condition, let's say some particular humidity and particular temperature. Then the bacteria can break this ketones down, and then you get back to individual monomers. And we know that if this polymer size is like because each monomer is let's say one molecule, and one small monomer, one unit. And if you have like 7 or 8 units, the bacteria can consume it as food, right? If it's very, very small, like you take CH, right? CH, 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 C double S, C, H, 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 like the 7 molecules or 8 molecules that can be consumed by bacteria as food, so they can destroy it. But if it is much longer than that, then they cannot. And one idea or one trick to do is to introduce this ketones, so that one kind of bacteria will break or eat these ketones, and then that will break up this molecule into small molecules, and then other bacteria can use it as food. So of course, there's many disadvantages, one mechanical properties, chemical properties. So we should keep working on this to improve that. That is one. The other one, since I'm part of this materials Institute for Materials Research, we are doing one part is energy, where we are making solar cells or things that needed for solar cells, and also batteries. And one part is materials, tissue engineering and stuff. So I am making this kind of polymer. So this is polyethylene oxide nanofibers, very small fibers. And one idea was to use it for transparent conducting electrodes. So actually, in the top of the solar cell, you want light to go through, but it should be an electrode. Means when the electrons gets produced inside, or holes gets produced inside the solar cell, they have to conduct in the top and the bottom. So bottom is, let's say, hole is conducting, in the top the electrons are being conducted. For that, you need some kind of conducting path. And typically now people use indium tin oxide, but it's a very rare earth material. And I think current estimate is like it'll last for like 20 years at this current rate where we are going. So one idea is to replace them with this kind of fibers. You can see through the meshes of the fiber, but these fibers themselves are conducting, because inside these fibers we add nanoparticles. We can add gold nanoparticles, copper nanoparticles, or silver nanoparticles. So this is gold nanoparticles, and now if an electron goes somewhere here, and it will just conduct through these wires, and that's a trick that we can use to make transparent conducting electrodes. I was involved. I'm currently not doing that much with this functionalized structural material. So many of this research is, of course, inspired by nature. One material that we do, or one functional structural material we do, is something called superhydrophobic material. So superhydrophobic means, like, hydrophobic is, hydro is water, phobic is basically it does not like water. So super means is absolutely does not like water. So one example is the lotus leaf. So if you put water on lotus leaf, it will either go in or go out. It does not stick there. It just flows out. The reason behind that is, if you actually zoom into this lotus leaf, and if you look into the cells, right? If you go and zoom in, there are structures, and the structures are at multiple levels, right? So these are structures which are 10 micrometer long. These are nanostructures, and these are some other kinds of structures. So this multi-layered structure, and it has some small oil coating on it. So it's hydrophobic. So, and then the structures will make them super hydrophobic. And the other one is this is actually a mosquito eye, eyes of a mosquito. And mosquito does not have eyelids. Like it can't, like we have eyelids, humans and other animals have eyelids. They don't have eyelids, but they stay close to water. They lay eggs in water. What will happen, because they also get foggy, right? So why doesn't they get foggy and cannot see it? Is because if you zoom in, they have this structures. See, again, it's something like this. These are really nanometer structures, and there's a big curvature on the eyes itself. So they really act as super hydrophobic, and that's why water will not stick to them. We replicated this structure, very similar to this structure, and then this is a drop of water falling on a super hydrophobic material, and you can see that the droplet is bouncing up and down, and it does not want to stick to the material, so it really bounces up and down. So this is one part of the research I was involved in. So this is three things that I was involved in, but now I'm going to talk about the research that, indeed, one part of the research that I'm doing currently with some PhD students and some postdoc. This is something on self-propulsion. So it's basically how bacteria propel. So we want to replicate it, simulate it, and try to make model systems out of it. One big thing that we are the first people to do it, is how to self-propel this rod-like particles on sideways. Normally, if there is a rod like that, particles will propel in the forward direction, but we are aiming to propel in the sideways direction. And we were the first guys in the world to do this. So now I'll go into detail what we have to do, how we have to think. Is also, I'm going to give you a slightly brief overview, right, of this, but because to probably I have to get into more detail of what is happening. I'll show you like what you can do. You can do experiments, you can do simulation, and you also how to think about experiments, how to tackle the problem. That is what I'm going to tell you now today. So there's a movie, just simple movie I'm going to show you. So that's how the particles are moving actually. So that's a dust particle. The one that you're seeing is dust particle, and you can see that this moving self-propulsion. Yeah, it's propelling on its own with some particular direction. It captures this dust particle and it starts moving. Right? This is what sideways self-propulsion means. These are the collaborators. So this is my postdoc supervisor and my colleague now, and this is my one of my friends, Jan from SAR. Venkat was the postdoc who was working with me, and now he is actually a professor in IIChE Bhopal. And we have a PhD student, Alina, Russian PhD student, Alina, who is carrying out further of what me and Venkat have done. And we have some funding for this research. So what is self-propulsion? We can see the self-propulsion in nature. So this is symmetric. So you take some colloids or some dust particles, you put it in water, they will jiggle around. They'll keep jiggling around, and I'm pretty sure in chemical engineering you heard about something called Brownian motion. It means like it's been hit by molecules, water molecules, randomly in different directions because of the energy, thermal energy that is there. And these particles will basically randomly move about. But on an average, they don't go anywhere. They move a bit this side, they move a bit that side. On an average, they are not going anywhere. They're just staying there. So this is symmetric. So because the bombardment is symmetric, it's random, but it's symmetrically bombarding in from all places. Of course, you can break the symmetry. Like this is bacteria, and you can see that they rotate, they propel, they're doing all kinds of things because they're able to break the symmetry. So they're able to, like swimming, they're able to swim in one particular direction. This is individual bacteria. You see they're nicely having some particular direction. They're going from place A to place B in general as compared to going nowhere there. And if you make this bacteria actually in high concentration, they start swarming. Right, so they have some kind of a ordered structure that's being created. Something is also true for bigger animals, also like fish and also birds and stuff. If you put them in huge quantities, they start to align and do things, not intentionally but unintentionally. The structures gets created. So now our idea is like we want to make something like this or this, where we break the symmetry and we are able to propel it. But the problem, one of the problems is like if you, I think your third year, fourth year engineering, right? There is something called Reynolds number. If you are at very low Reynolds number, then you can't propel yourself. You can't do symmetric propulsion. So basically, you are going to swim. So I'm going to show it, seeing my video. What you do is swim. You go forward, then you push water, then go forward, push water. If you are at low Reynolds number, it either your viscosity is higher or your size is very, very small, because that's the Reynolds number, right? So velocity, length, kind of divided by the kinematic viscosity. If you do like this and go back to do the swimming motion, you are not going to go anywhere. You are like this Brownian motion. You go back and front, back and front, back and front. In water, you are able to swim because there is something called inertia. So water has low viscosity, and of course your body size is high. It's because when you go up with your hands, you go slowly, and when you push water down, you push it at very fast. So there is a lot of velocity. So the inertia is there, and you move forward. In the low Reynolds number, you can't do this. Any symmetric motion, you're going to move forward, come back, move forward, come back. So here is an example. If you are not seeing these videos by a guy called G.I. Taylor, I advise it's free, available online, YouTube. Look at fluid mechanics videos. G.I. Taylor, extremely good videos from 1970s. So what he has done is basically he has taken high viscous syrup here. So it's very high viscosity. He's going to place a boat, which basically like a fish does symmetric motion, right? It does like this. So if you do like this, it goes a bit forward. If you do like this, it goes back forward. And then later on, you put something that is like a spiral, and you'll see that what is going to happen. Right, so this is in water. So currently in water, of course, in water, if you push like this, you are going forward because of inertia.
Owing to the reversibility of low Reynolds number flow, the forward motion of the blade is neutralized by the backward motion.
So it's not moving anywhere, right? So going down because the gravity is pulling it down. But in general, it's
This spiral model does swim. Each element of the spiral is behaving like the obliquely falling rod. Because lateral resistance is greater than longitudinal, motion at right angles to the axis of the spiral can contribute to a longitudinal component. The spirals are right and left-handed to keep the model from rotating.
See, now if he has put the spirals now, so spirals has some motion, it breaks the symmetry, so it can go in one direction as compared to the other one. So two things you have to think for cell propulsion. One is you have to break the symmetry. Right? That's the first one. That's what we had to. That was the problem, right? We had to come up with an idea saying how can we break the symmetry. And second thing is like how can we propel? What is here? The propulsion is mechanical, right? It's either moving like this or doing the spiral. In my case, it'll be some kind of a chemical reaction that is happening on top of the surface due to catalytic reaction with hydrogen peroxide, and that propels the okay. So people have had done it. So in 2002 they had done this. So basically they have taken a plastic sheet, they put a glass plate which is covered with platinum. Platinum is the catalyst, and you put it in water with hydrogen peroxide. It starts making bubbles, and then that bubbles will propel it. Right, bubbles will come, burst, and then they propel it. And then people went on to do many other things. One is you take a sphere, you coat half of it with platinum, another half is just a polymer, and then you put it in hydrogen peroxide solution. They start propelling because one side you're breaking the symmetry, right? One side there is a reaction, other side there's no reaction. You create oxygen molecules, and there's a diffusion gradient between oxygen rich and oxygen poor sides of the particle, and that kind of moves the particle in one direction. You can also make rods. So this is a rod made from two materials, I think platinum, ruthenium, and platinum, or platinum, gold, and platinum. And these rods propel in the forward direction, right? They are along the long axis, and you can see that they actually move, again, based on hydrogen peroxide, or also you can use some other things like glucose and stuff. So people have done this cargo transport. This is where I came in. This is what I saw, and I wanted to solve the problem. If a rod is propelling along the long axis, it can carry at most one or two particles, right? And if you have a big rod, of course, it can carry slightly bit more particles. You can see that this rod, you can see again, it will come back. This rod is carrying one particle at some point, then it leaves it, and then it goes out, right? So these are just Brownian particles that are moving in. You can use basically a sphere. See on the top of the sphere, they are collecting rods. You can see particles. They're collecting particles that can also push. But if, of course, the rods can be much more efficient, the only thing you need to do now, we have to do was like the rods propel in the sideways. You can use it as a shovel, right, as a pushing thing, and then it can push or pull the particles like this, and you can collect a lot more particles much more efficiently than this way or this way. That was the question. Can we do this? People have done this. Can we do this? This was the question that we were asking. And what is as I told, like I'm going to give you how the thought process went. First thing, can we make the rods that can propel sideways? First question is like, okay, what are the requirements? First requirement is we need to make a rod, of course. And these rods has to be, this is self-propelling. I want to replicate bacteria and stuff. So the easiest way you have to do is like you have to go in micrometer, at least micrometer. So I should be able to make polymer rods from micrometers or metal rods from micrometers. So first one is that. Second one, I should be able to break the symmetry, right? I should make it. Janus means two faces, right? That's a Greek word meaning two faces. So you need to break the symmetry. It means like you need to put one material on this side, that other material on that side, right? That's how you break the symmetry. So you have to make the rod, and then you have to make the symmetry. Then you go in your lab or you go in your neighbor's lab and you look what they have and try to see what you can do. So it was like, so one was I was already working on this electrospinning to make the fibers. I thought, oh, maybe I can use the fibers to make it. So you make electrospinning. So easiest way is like you push the solution here, you put a very high electric field, the droplet gets pulled, which has polymers in it. While it's going, it evaporates. Mostly we use ethanol or dichloromethane. They evaporate very, very fast into the atmosphere. By the time this jet comes here, all solvents are evaporated and you only get polymer fibers here. So this is one method to make this thing. How can make the symmetry? I was using something called scanning electron microscope. And to do a good scanning electron microscope, you have to coat the material with some kind of a metal layer so that when the electron hits the material layer, some of them come out, and the ones that are going into the material has to go somewhere out, or else it'll kind of charge. So electrostatics, so statics will build up, and then you're not going to get a good image. So you need to put a small metal layer so that the electrons can conduct to the metal layer and can go into the ground. So I know, okay, now I can make the fibers, right? I can make these rods. I can have to think how to cut them. That's a different next step. But I can make the rods and I can go into this material and I can put it one side, I put gold, I flip it over, on the other side, I put platinum. So now I'm making the symmetry also. So I'll slightly deviate here and tell you like what is electrospinning, what can we do and stuff. But again, this mostly the idea is to show you, once you have the idea, how you can proceed, right, when you're doing research. So how the electrospinning works, as I told, right, you put a polymer solution here, you mix polymer in water or DMF or something like that, nicely let it dissolve, you slowly push the solution, you put a high voltage between the top needle and the bottom plate, and the electric force is so high that you have to go to very high electric fields like 20, 30 kilovolts. So you have a very high gradient, electrical gradient here that pulls the polymer solution out. It's called Taylor cone, the same guy that I was mentioning, his name. Then it starts bending and whipping, it's becoming thinner and thinner. And of course, the solvent is also evaporating. By the time it hits here, it's almost all solvent is evaporated. And based on the characteristic of the polymer, how long is the polymer, what is the concentration of the polymer, what kind of solvent we use, we either get this kind of beads, or we get this kind of beads on string, or we get these fibers. And of course, my aim was to get to this fiber. So I had to use either high molecular weight polymers, like polymers which are very, very long, or use slightly higher concentration of this same material. Right, that's how the jet looks like. And now you can see the jet. So basically, you put very high electric field, jet is being pulled. Initially, it's straight. After some time, it starts bending. It's the same thing when you take honey and you pour it from top, you'll see that at some point it starts bending. And this bending instability causes it to become thinner and thinner and thinner. And at the same time, it's evaporating. And this is called Taylor cone, named after that guy that we saw the video on. This is the equipment. This is how the equipment will look like. This is how the polymer will look like. See, it's not a good way. We also have to think, how can I now put this polymers in a layered way so that I can coat one side with platinum, flip it over, other side with gold, and then break it up. This will look like. Oh, did I go off now?
Yeah.
Okay. Sorry, I will come back again. That's why I told, probably my internet is great. Okay, let's try again. Okay. Okay. So now I'm back?
Yes.
Okay.
Yes, you are back.
Yeah. So it might fall down. If I fall down, please let me know if I don't see it by chance. So that's how the thing that I told you, right? So when does a fiber form? Either you should have a very high molecular weight, that green color that you're seeing there, or you should have, if you have a red color one, which is a low molecular weight, then you should have a lot of concentration of polymer. So one trick you can do to kind of, because if you put too much polymer, then the viscosity will become very high. It will become like honey, and then you cannot pull the polymer down. But if you have low concentration, then you don't get the fiber. So one trick you can do is this blue color. You use a lot of low molecular weight polymer, so your viscosity is less, like it will be like water. But add a very, very small amount of this high molecular weight polymer, which is the second peak in the blue. And then if you mix the two, you're going to get fibers. So that's the trick that we used to do this. So there's I'm going to show you a couple of images there, right? So how the electrospinning, or how we can make fibers based on different sizes of molecular weight. So one is this 370. So 370 is just a number, 370 methyl methacrylic polymer is there. It's in a solvent that evaporates very, very fast. It's called acetylene. What I have plotted here is concentration in milligram per milliliter as a function of molecular weight, as the length of the molecule. And we know from literature and from what people have done is, like, if you're above this line, it's called a C-star line. It means like if you keep adding polymer to your solution, at some point you add so much that they start touching each other, right? They're touching, so it becomes something like this. They're touching each other. Then it's called overlap concentration. So they're overlapping with one another. If they're far apart from one another, then it's basically dilute. They know that if you're above this, you'll start forming fibers. If you're below this, you're not going to get fibers. So we were below this, we don't see any fibers. We are below here, we don't see any fibers. And we go just cross the line, we barely start seeing the fibers here. So in theory, this theory is good. You go to higher molecular weight concentration, you see that for the lowest concentration, we don't see any fibers. If you go slightly above, we start seeing fibers, even though we are below this line. And of course, if you go close to the line, you get a lot of fibers. And now the molecular weight is 770. That's double that what previously we had seen here. And if you go even increase it even higher, like 1700 kilodalton, then even for very low concentration, which is almost 5 milligram per milliliter, you already start seeing the fibers. And of course, if you go over the line, you see huge amount of fibers there. So it means like the theory says that, but when you do experiments, you see that there is also some kind of a scaling coming here. And that is what we did. So we knew that, okay, this is what old theory says. And from experiments, we know that there should be a line here. And if you plot that line, that comes as molecular weight to the power of minus 1.5. That's how it looks like. Now we need to explain why this is 1.5 and what is the explanation behind it. And for this, of course, you need to do some theory. And also we did some theory with a professor in MIT. Basically, there's something to do with polymers. I'm not going to explain to you in details. If somebody is interested, let me know. Basically, when the polymer, you put a polymer, it's like a coil. The coil size is this R square. That describes the coil size. Actually, when you stretch, you take it and you pull it. Then the maximum size, and this, you can't make it completely straight because there is something called bond angles, and it has to be like this. This is the maximum stretch. And then you can, using these two parameters, you can define something called extensibility. And that extensibility will give you some kind of a parameter, molecular weight to the power of this mu. This mu is nothing but solvent quality. Does the polymer like the solvent? If it likes the solvent, then it opens up. If it does not like the polymer, then it will be like this. Right? So it's basically like that. And then there's something called dumbbell kinetic theory. From that, you can also calculate something called extensional viscosity that depends on the polymer viscosity and this extensibility factor. And the polymer viscosity depends on the viscosity of your solvent. If it's ethanol, viscosity of ethanol. Something called intrinsic viscosity, which depends on the molecular weight. And the concentration, how much amount of polymer that you put in. And you put all this together, then you're going to get extensional viscosity as some kind of a function of molecular weight, what kind of solvent it is, does the molecules like the solvent or not, that number tells you that, and the concentration. So you combine these two, and you make a hypothesis. Always when you're doing research, you have to make an hypothesis. And the hypothesis is, our hypothesis, there is a minimum extensional viscosity that is needed to get the fibers. You take these both equations, you combine, this is just an algebra. You will get like to make the fibers, the minimum concentration goes as molecular weight to the power of solvent quality plus. I'm hearing the echo. You guys are fine. I'm just saying if your Anil is hearing me. Okay, it's fine.
Fine. Okay. You can proceed.
So once you get this kind of formula, right, you have to say, have people have published a lot of the literature. Does it correspond to the what people have published in literature? You start looking for literature values. So this is my data. So this is what my data looks like. That's how the slope looks like, right? That's the equation that we finally found, right? And then you go in literature and you see all other people, right? So this is PS, means polystyrene in some solvent. Some other people have done same polymer as me, PMMA in DMF. Some other people have done PVA, polyvinyl acetate in water. And if you see at the end, all of them show this slopes. And then that is the solvent quality that is there here. This almost approximately everything is around 5 point plus. So they're all good solvents. And now if you take this, all these lines are coming like this. So you pick the molecular weight, you pick your solvent quality +1, and you get these lines. So it means like the theory and experiments seem to match. And then you can go back and go back to my experiment that I was there, right? So this is 540 now, some other molecular weight I took, and then this is how the curve looks like. Right, I'm here. So if you see all the thing, and then this is the slope that I'm getting, molecular weight to the power of 1.58. So I'm able to define it nicely. And then we have to define something called extensibility average molecular weight. So you define, again, this is algebra, I'll not go into detail. Finally, we are going to get this. So how much the molecule can extend, that's what basically is extensibility molecular weight. Effectively, what is the molecular weight? So it goes as some kind of a weight fraction to the molecular weight to the power of some kind of a solvent quality. And then this is how it looks like. So you plot concentration as a function of normal length of the molecule. That's how the curve looks like. And then if you use it, this extensibility, average molecular weight, new definition of molecular weight, then you see that this dots move a bit. Then you say, oh, this is maybe just a fluke. It's not that far away from each other. So you may be just lucky. So again, you have to make an hypothesis, and then you have to confirm with your experiments. We can do one more trick. What we can do is, like, we can make a blend now of very low molecular weight and very high molecular weight. Lot of low molecular weight and a very small amount of high molecular weight. And now if you take, this is how it looks like. Here it is. So here is the thing. So I took a line here. That is the molecular weight 130. And that's the molecular weight 1700 kilodaltons. And then I can take, if I combine them, my molecular weight, effective molecular weight would be this one. So I get fibers here, I get fibers here, I get no fibers here. But I'm below this, but I have to be at that line. But instead of molecular weight, now I will change it into extensibility average molecular weight. And if I do that, you will see that this molecule and that molecule will go there. Right, so there's a shift in the thing. Now my theory predicts exactly what my experiments is showing, which is pretty good. And then this is what we figured out. So previous scaling law was saying that if you are above this red line, you get fibers. Below the red line, you don't get fibers. But now we found out that actually there is a region where if you have this high molecular weight polymers, then you will get these fibers in this green region also. So this is very useful for my transparent conducting electrodes, where I want to make mostly from this metals and very small amount of polymer. So my trick was you use very small amount of high molecular weight polymer, you add this nanoparticles, gold nanoparticles, and you can make fibers. If we did not have this, and we had to do here only in that region, previous region, then we could not have had what the results that I got here. And if you want more details, of course, you can go to this paper and look at this paper to study in more detail. Okay, now this is the part of the fiber, how to make the fibers. We'll go back to my self-propulsion now. So we make the fibers, we know how to make the fibers, exactly what is the length and what is the concentration that we need to make the fibers. Now we need to make them Janus. Yeah, we have to coat one side with platinum, the other side with gold, two materials. So for that, we use this kind of a plate, because we need to be able to flip the fibers in this putter coater. This side coat the top side, flip it, coat in the other side. You take this, you make electrospinning. By accidentally, randomly, they go up and down like this. We can also control by changing the voltage or altering the voltage between these two plates. Then you need to cut this here, and this is how the fibers will look like. This is a normal image, and then if you go in the scanning electron microscope, you will see that you're going to get more or less straight aligned fibers. Now you coat one side gold, flip it over, coat other side with platinum. And these are all the conditions that we did. And then you need to see, once you coat it, you have to see, is the coating good? Is it attached to the polymer or not? So this is a scanning, this is a transmission electron microscope. As well, the electrons are going in, transmitted. So you can see that side is basically platinum, and this side is gold, and this side is platinum, that side is gold. So that is how you coat the material, and you can see that it's there. Once now we made the fibers, we have coated on both sides. Now we need to break. We have to do two kinds of things we can use. You just take this fibers, you put in a sonication bath, and you bake it randomly. One advantage is you get all kinds of sizes of fibers. So in one experiment, you can do actually a lot of data collection because different sizes of particles, but there is no one size that you can repeat. You want to test it like, oh, can I do it 3 times, 4 times just to make sure that it is correct what you are getting? Then you basically cannot use this one. Then we go for laser cutting, where we cut these fibers in laser and we can get exactly the length. So this is approximately like 60, 70 micrometers, and that's the length that you're going to get. So we wanted to know that if the material that is there, is it catalytic? So for that, we can put it as hydrogen peroxide, but is it conducting? Right? Because we want to make sure that it's completely covered. And then this is how it looks like. So the material, here is the gold part. It is big chunks. It comes as 5 nanometer when you sputter. And the platinum side, because whenever you sputter coat platinum, there's a small amount of palladium they add like a softener, and it makes the particles that comes out of the sputter coater into soft material. And then this is electrical things. So I'm a chemical engineer. You need some electrical things also. You have to go to the electrical friends and ask them. This is IV, current and voltage. And if you have a linear relationship, then you have very good conductivity. This is one of the highest material. Then platinum, the gold looks straight here, but if you zoom in, you'll see that it's also linear. And then you see that, okay, everything is coated. And we published this in this journal if you want to look into more detail. So now we made the fibers, we coated it in 2 sides, we made it Janus, and then we broke it now. Right now we are going to do the test of self-propulsion test. So one is you take this is condition without. Yeah.
Dr. Naveen, can we wind up in 5 minutes?
Yeah, we can finish. Yeah, should be okay. Yeah, I think 5 minutes should be good. I think almost there. We are there. So this is a condition without hydrogen peroxide. It means like there is no catalytic activity. It's only water. And if you see that, that's how the particles act. They're not going anywhere, right? Brownian motion, right? They're not going anywhere. Now you put them in hydrogen peroxide solution, this right side picture, and you see that they're propelling in a sideways, right? They're going in a sideways direction. So we have that, then we need to kind of explain. So this is the kind of explanation that we gave, why this is happening. You can again go to this paper and look into this. You can do a lot of analysis to this to see that if you place something called mean square displacement as a function of time, if you get a slope 1, that's Brownian motion. If you get a slope 2, it means like it's going at some particular direction and it is non-Brownian anymore. And then you can make this for straight particles. We can make it for different kinds of particles now because we are making different shapes. So straight particle, of course, is going to go straight, right? Because it's symmetric. Pushing left side, right side is both the same. There's a slightly curved particle, but still symmetric in the center. So it also goes straight. This is a V-shaped particle, but also the shape, the V, the arm, one arm and the other arm is exactly the same length approximately. So it also goes straight. But if you have something that is asymmetrical in the length, so one arm is less and the other arm is less, it starts making rotation. And of course, you can go into theory. This is what my postdoc did, Venkat. So he went to theory, he made some kind of a beats model. I will not get into the details. And this is how you can do. So this the red color is the experiments. So that's the experiments, right? Rotation experiments. And when we do some theory with modeling, beats model, then we get this blue color, which matches more or less very good with the experimental details. So simple model, a lot of assumptions, still we are able to capture it. And I have this last transfer property, I think 1 minute and we are done. This is what the image I showed you at the beginning, right? This is where we wanted to do these experiments. So it goes, captures one particle and stuff. What now if I want to transport a lot of cargo materials? That's an example. So you're seeing that this is the rod, and you can see huge particles is being captured and is being pushed to the side. So that was the goal at the initially, and this is the result. So I think with this, let me end, and I'll thank Anil and Anish for letting me talk with you guys. And if you have any questions, please let me talk to me now or ask Anil for my email. And you can definitely email. But when you email, please email me saying that in the title you put Anil, so that I know that you're an Anil student and I can respond to you much more better.
Participants, now you can stop sharing so that you can start.
Stop sharing.
Okay, yeah.
Okay. Now I should.
At the top, you'll have.
Okay. I have list, and I say that one.
Yeah.
Oh. They will stop
Yes,
on.
yes.
Yeah. Okay.
Yeah.
That's good. I think I stopped sharing now.
Yeah. Anil sir, continue.
Yeah, participant can post their questions such that Dr. Naveen will be answering them now itself. So let's wait. Someone.
So Naveen sir, one question I have from my side.
Yeah.
So the bubbles bumping down and up, and then sticking to the surface. So can I?
They're not sticking. It's just gravity holds it, but it does not stick to that.
Okay. So can I do that for any virus cell interactions? Those studies, can I correlate these virus cell interactions?
Okay. So for virus cell interaction, this might not work because the length scale that you saw in the picture, right? The droplet is around 5 millimeter in size.
Okay.
It's a big droplet.
Okay.
And the superhydrophobic material is a big material, so you can't kind of do it. If you want, there are people who are trying to kind of do this to remove dust and also viruses and bacteria, if that's possible, because virus is too small, so maybe the size scale might not work. But dust and bacteria is for sure. Is that if you want to clean the surface, you can make it super hydrophobic, and then if you drop water on top of it, it will just take away all the dust and everything that is there, which is what actually the principle of Lotus works on, because it always makes sure that its surface is clean.
Yes. And one question from the student side is that can the students have summer internships in Europe for 1 or 2 months?
Yes, they can, but they have to come with their own funding.
Okay.
Because in Europe, the masters is actually government paid masters. So actually, as I told you, right, in Europe, especially mainland Europe, 99% of the universities are government universities. There is also schools are government schools. There is no private schools, no government private universities. So that's why the tax is high. So you pay very high tax so that your kids can go to school free. So I don't pay any fees to my kids. And in the university also, kids generally don't get don't have any fees. So they can come, but they have to pay they don't have to pay any fees or anything. They just their flight charge and their staying cost they have to bear. And then you just contact us. So we were supposed to actually now have a student from IIChE with her own funding. She was coming here to do exactly actually this research, what I told you now. She wanted to do some side track of this for 2 months, but because of this coronavirus, we have now postponed it to next year.
Okay.
But before you come, you have to write an email to the let's say to the professors. Mostly it's professors. It's not the universities, but it's the professors. But we do get now master students or bachelor students for research for 6 months from Brazil. We get like 10 students every year from Brazil approximately, and every year I get one student now. But they also get funded from the Belgian government, Brazil government, and or their own funding. So now I think one student is coming He's going to land in 2 weeks and then be in quarantine for 2 weeks to make sure he does not have COVID, and then he's going to start the research in September.
It's true. So the questions are open. Floor is open for the students. You can unmute and you can ask the question.
I think somebody wrote an email saying like, can you give us the links for these publications? If you go to if you type my name, Naveen Reddy, you hustled, Google Scholar, right? You will get all my publications, whatever I have published. So you can ask any question, so don't be shy or anything. You ask anything that you want, not only related to education, about something totally that you want. So because you never know what questions, which will also help other students. Some students might be shy to ask, so please type. So typing is okay.
Sir, good afternoon, sir. My name is Ravi.
Yeah, tell me.
Sir, actually, sir, so do we really need to know other languages, sir, like German or Dutch, to do our masters in European countries, sir?
Yeah, masters, it might be in Germany, because Germans are bit like very strongly in language holders. So some of the universities do provide English masters, but some of, I think Germany is like this 50%. So 50% is in Germany and for German, and 50% in English. But there are some specific masters which you can do it which you can do in English. But most of them are in German. And France, 99.9% of masters is in French.
Yes, sir. Belgium also is the situation is same, sir, or we can come with our English?
No, Belgium, all masters in Belgium is in English now. I think last 5 or 6 years back they changed. All masters in Belgium is in English, and Netherlands also. Netherlands, Belgium is all masters in English. I think Sweden also same thing. I think Sweden and probably Switzerland also partly like Germany.
Okay, sir. Thank you, sir.
Yeah, and the living expenses, I don't know if somebody is interested. So living expenses typically will cost you around 500 euros. Rent, if a student hostel would be around 200, 300 euros, depending on if you get a subsidized rooms from the university, or you go to the private rooms, and your eating cost and stuff would be around 200 euros. So it's 500 euros. That's like 40,000 rupees per month. And your fees would be relatively less, around 3,000, 5,000 euros or something, which is 2-3 lakhs, which I'm pretty sure in India is as expensive as in Belgium now.
So would you recommend for MS aspirants to take Belgium, sir, or some European countries like Netherlands, Sweden?
No, any because it depends on what interest you are. If you go to so because I am Belgium, so I can talk about Belgium, and I am also slightly biased that to tell you that you can come to Belgium. But I told you, right, Belgium, Netherlands, Sweden, Switzerland, and Denmark. So these 5 countries are pretty good. And somebody is asking, like, do you get scholarship? For masters, you don't get scholarship, because especially here in unless you come with this Erasmus program. You can look, people can look Erasmus, ERSUMS, Erasmus program. So I know many Indian students, from many years are coming via this Erasmus program, where they do pay you the scholarship. That is one advantage. Or else you have to go to either Canada or US, where you have to go to masters, research based masters, because then they get money for research and they will get you a scholarship. And nowhere else the masters is for free, and you don't get scholarship for masters actually. And especially in Europe, you don't get it other than this Erasmus, is just because masters is considered as a basic education necessity, and the local people will not pay any fees for it actually. Anyway, they pay like 100 euros, like 8,000 rupees or something, just for namesake, because their parents and grandparents are paying a lot of taxes. The education is free. And since you come from abroad, they give you a nominal fee of around 3,000 or 5,000 in Belgium, I think Netherlands is like 8 to 10,000. UK might be a bit more, like 10, 15,000 pounds. Sweden, there all is again minimum, like 3,000, 4,000, something like that. It's almost the cost of your flight cost, up and down a couple of times. Somebody told, sir, I am second year student. Maybe you can ask me the question. Because the thing comes, but I cannot click on the text. Somebody was asking, I'm a second year.
She's asking what kind of internship can be done during my second year.
So second year internship, if you internship means normally, so you have to be also careful. One thing you have to watch out is in India, I don't know when you guys have holidays, right? In between semesters, when is that semester break that you are having in India?
Sir, usually we have only for 15 days for after first semester. But after
because typically the internship, they advise you if you come for internship, then you come for a month or 2 months. 2 months is really ideal to at least so that you because if you come for a month, it takes you for a week to get used, and 2 weeks you work, and after 1 week after that you are already in the mood to go home.
Yeah.
So ideally 2 months if you come, that's very good. And when you come here, most of the time it's better that you do some research, because teaching wise, you will be in between the semesters or something for you, because here the semester ends in June. So July, August is a summer holiday here, 2 months. And then the next semester begins in September. And again, December 25th to January 10th or something is one more winter break between semesters again. So if you come, the ideal time to come is to come July, August. So it's also free. You will also get hostels here because most of the students would have gone, all the bachelor's students. So you will also get a hostel that's relatively cheaper from the university itself. And professors will be relatively free to, or PhD students will be relatively free because there will be no teaching. They can guide you a bit in research if you come in these 2 months, July, August.
So anything more? Like
is Belgian dark chocolate can cure? What is it?
Can cure heart diseases, or it's a hoax?
No. So I don't know if it can cure heart diseases, but they do say that dark chocolate is basically chocolate, right? Dark chocolate is chocolate without sugar or milk. Bit sugar, but not milk. So dark chocolate is known to be good for health. Not too much, because if you eat too much, then your liver cannot handle it, and you'll have a lot of issues with your liver. But typically they advise, which is also probably a bit of marketing, but research-wise, it is known that eating, let's say, 2 centimeter by 2 centimeter or 4 centimeter by 4 centimeter dark chocolate every day is good for health. But do check, because they have a huge amount of calories, because they add. In general, you can't eat chocolate. Chocolate is a bitter. I think it's a fruit, right? So chocolate, bitter seed, a bitter fruit. And the Indian Americans were chewing it. Actually, Mayans and Aztec people were chewing it as betel nut. What we chew, they were chewing it, but it's bitter. So the darker you go, bitter it is. But of course, it's healthy. In general, healthier because it's less milk and less sugar. That's the reason, I think. Anything else? Also, by the way, Belgium is also famous for chocolates, chemicals, pharmaceuticals, plastics, diamonds, and beer. Yeah, his experience
plays a major role in working at abroad, and is there any possibility to get projects from abroad industries?
To India, you mean?
Yeah, to India. Yeah.
Oh, that's very rare that you get projects from other countries from between different countries. Very, very rare. Experience, of course, if you want to move around, it's better to, I would advise, if let's say you go to industry, you work there, you have a couple of 4 or 5 years of experience, And then within the industry, if you want to jump, you can jump to some other country and then you can go like that. But it's very rare that somebody directly applies from India to Belgium or to Netherlands or to US and jumps industry jumping. That's very, very rare. Generally what they do is like they jump within the company to different place. And once they are there, then they jump to some other place. That's much more easier.
Yeah.
One
One more student is asking like, where should I apply for the internship? Is there any any particular website or so?
You have to write to the professor.
Okay.
That's the only way. Though in US, I know that a lot of internships programs are running in US. I know a lot of IIT students go there. So they're very, very good with internship. And sometimes you may get scholarship and stuff. But in Europe, no. So not that many internship students come, but if they come, of course, they come on their own. But professor, because they're the one who is going to make the decision. Once they make the decision, then they will ask the university HR department to take over and handle all the papers and visa and all these things.
Okay. So anything?
I think one more question, something is there. Somebody asked something, one more question was there.
It's here, it's about your journal only. So
yeah.
My colleague answered it, right? He said,
okay.
Google Scholar, go to Google
Scholar. Naveen Reddy, you hustled. I think I'm the only guy who's going to come. I think before that, there was one more question. I think somebody asked me some.
That's it. It's about internship only.
Okay.
Yeah, that's it. So
I advise your students, like give them my email and they can email me putting your name in the title so that I know that it's your students, and then they can ask me any general question and I'll try to answer as much as I know.
Yeah, definitely we'll do it. So anything more, or shall we wind up?
Anil sir, wind up.
Yeah, fine. One more question is there, Shivanaresh. So someone is asking,
what is the scope of this research paper?
What is the scope of
this research paper? I don't know what research paper.
What research paper?
Nokaraju, can you elaborate what is the type? What is the scope of the research paper? Nokaraju, elaborate your question.
You can talk directly. It's also okay.
Yeah. Nokaraju, unmute.
I think he's
okay,
not
Naveen,
there.
I think he can mail you about his question. I think he's...
Yeah, that will be fine.
Yeah. So thank you everyone for participating, and thank you Naveen for explaining beautifully the research going on polymers at Belgium, and then the other important thing, how to get into Europe for masters, right? Because most of the Indians, they want to go for masters and then go abroad and settle there. So that is because engineering is famous for that, because most of them they go abroad and then settle down. I hope our students will be utilizing this opportunity to grab more MS in recent years, right? I once again thank you on behalf of ANITS for giving a talk in this.
No problem.
Yeah. Thank you, Naveen. Thank you.
Okay.
Thank you.
Ciao. Bye. Good luck.
Yeah.
Be safe. Be safe.
Yeah.
Thanks, Anil.
Thank you.
Bye.